Welcome back, everyone. In this video, I will begin going over the lecture for exponential growth and decay. Now, what we do in this section, the problems that we do are very similar to problems that you may have seen in a previous course, like a pre-calculus or algebra type of course. And you probably talked about things like half-life, doubling time, just exponential growth in general. And we're pretty much doing the same thing. But in this section, we're going to have a deeper understanding of why exponential growth is what it is, because we understand what the derivative is now, why it's actually called exponential growth. All right, so first we're going to just talk about the formula of exponential growth and decay, where it comes from, and then we'll work some problems with it. And then in the second part of the section, we'll actually see a slight variation. You may have heard of something called Newton's law of cooling. It's basically the same formula as exponential growth or decay, but because you want something to happen slightly differently, there's a slightly different formula for it, and we'll understand where that formula comes from and how it works and all that stuff. All right, so first off, I want to go ahead and start with exactly what we said. What is the formula for exponential growth and decay? Well, the main thing is that it actually comes from what's called a differential equation. Now, differential equation, that's something you won't be really exposed to and asked to solve until Calculus 2. And then also there's many differential equation classes that you can take after Calculus 2 or Calculus 3 as well if you wanted to. But the main idea here is that just kind of expose you to where exponential functions come from, exponential growth and decay. So the setup is like this. It says a function y of a variable t is said to have exponential rate of change if it satisfies the following. Now really there's only one formula, and that's the one on the left here. It says dy over dt, so the derivative of y with respect to t, because our variable is t here, equals some number k, this is just a number, times y. Now, when you read this, what it's actually telling you is that if you do the derivative of your function, what you get back is just a number times your original function, because that is what y is representing. And I think this, is a very important aspect of exponential growth or decay, is understanding why you use these formulas and where they come from. Well, it comes basically because if you do the derivative of some function and you get back just a number times your function itself, then your function is said to have exponential rate of change. Now, some people will rearrange this by dividing each side by y or multiplying by 1 over y, and they'll view it as 1 over y times dy over dt. So you can kind of read this as the derivative divided by the function itself equals a number. Now, I don't really like this one as much just because it's hard to read, but it can give you some understanding about why they use this terminology. So k is a constant, it's just a number like we described. And a lot of times, especially if you want it to be described in a problem where you don't know if there is actual exponential growth or decay, you have to be told it's something called like a constant relative growth rate. Relative comes from the fact that it's a fraction. You're doing the derivative divided by the original function, and that's exactly what it equals. But once again, we just kind of want to know why exponential functions come or where they come from. We don't really want to try to solve this because we can't solve it. This is a calculus 2 problem at minimum of being able to solve this for y. But another couple other things of terminology. If k is positive, so if k is greater than 0, then what's happening is your exponential function is growing. So this is the law of natural growth. And if k is negative, this is the law of natural decay. But the point is they're going to be the same exact formula, just depending on whether k is positive or negative will give you everything you need to know. Right? So the main theorem here, and I kind of mentioned this before when we talked about the derivative of e to the x, is that the derivative of e to the x is itself. Well, the only solutions to this, so reading this again, we do the derivative, it equals a number times the original function. The only solutions to the equation dy over dt are the exponential functions. Now I have it written in a particular way. It says y of t equals y of 0 e to the kt. Y of 0 is just the function itself evaluated at 0. And typically that we think of that as like the starting or initial amount of whatever we're doing, because it's at t equals 0. But what I wanted to go ahead and do is just show you that this is true. Now, one thing I'll mention is that we can't actually prove the only part, but we can prove that this is a solution, meaning if we do the derivative of our function, we'll just get the function back times the number k here. So let's go ahead and do it. I'm going to go ahead and do dy over dt. Well, y of t, the function is given by this formula. So when I say this, I want to do d over dt of the function over here, y of 0, e to the kt. And we know from our vast experience of derivatives that y of 0, or anything without t, is just a number. Y of 0 is our function evaluated at 0. So like you know, if you take a function, you plug in a number, you get out a number. So as our derivative properties say, we can take this y of 0 and we can bring it out because it's just a number and it's multiplied. So we get y of 0. And then we still have the rest in there because the t is in the exponent. So we have to do the derivative with respect to t of e to the kt. And now k is also just a number, but can't be brought out because it's stuck in the exponent. But we can just use the chain rule here and do this derivative. We have the y0 up front, the derivative of e to the something. With the chain rule, you start with the exactly itself, and then you multiply by the derivative of the exponent with respect to t. And the derivative of k times t is just k, because the derivative of t is 1 and k is just a number. If you're not seeing it right away, maybe think about what if k was 2? What would your derivative be? It would be e to the 2t times the 2. Okay. But the point here is that what we just figured out is exactly what I set out to show you, because what you have right here, this is just what y or y of t is. So it equals y times, y times k. And that's exactly what we wanted to show. The derivative of the function equals the function itself times that number k. All right, so anything written like this, any function at all that's written of this form, when you do its derivative, you just get itself back times k, and it has what we call exponential rate of change, growth or decay. Now, a couple things I want to go ahead and mention is that when we're dealing with problems, we're probably not going to use the letter y very much because we're going to be doing word problems. And in word problems, we're going to be representing specific things like exponential decay. Radioactive decay is one of the common ones. Usually talk about mass. So instead of y, we would have like m or something. You can talk about the population, maybe population of bacteria, because bacteria typically grows with exponential growth. The more bacteria it is, the more there is to grow. Or even things like money, because compound interest also is something represented by exponential growth. Those are the three main things. Now, one thing I want to go ahead and mention, because there is a second half to this section, is that this formula for y of t, let me bring it back up here. When you do the limit of it, let me go ahead and actually write it down on the side here. This is a very important aspect. The limit as t goes to infinity of y of t. So I'm going to plug in the formula here for y of t. Y of 0, e to the kt. Well, it equals two things depending on what k is. If it equals infinity if k is greater than 0, and it equals 0 if k is less than 0. Now, why is that important? That's important because what's happening here, if you think about t being time, saying the limit as t goes to infinity means t's going forever. Time is going forever. So if you just had the setup of the problem and something was going on forever, if k was positive, then let's say it's money. So money is growing in a bank account, then it's going to shoot up to infinity if it could go on forever. And in theory, that makes sense. And if k is negative, like exponential decay, you could think about radioactive decay. Eventually, the amount of mass goes to zero. So that's an important aspect of these formulas. And if you want to, actually, I can go ahead and do it. Just to remind you, this really only comes from the fact that the limit of e to the x is either equal to infinity or zero as x goes to infinity. But let's go ahead and just take Desmos here so you can see. I'm going to use y of 0 equals 1, so I can just completely ignore that. And for k being negative, I'll do -1 for that example. So e to the negative t. So for that one, like I said, this is when k is negative. And you can see as t, this is the t-axis here. As it goes towards infinity, we're pretty much getting the y value of 0. Well, now if I make k equal to 1, so it's positive, I'm going to delete this minus sign. Then as we go to infinity, it's just going up and it's going to shoot up forever. You should know the basic graph of e to the x by now, and it's going to infinity. Well, if you have physical things that don't make sense like this, for example, what we'll see in the second half of the section, if you have something that you're cooking, let's say you are cooking a turkey, because that's something I can think of right away. After it cooks, it's way too hot to eat, but it has to get that hot to actually cook through. You put it out on the table and it starts to cool. Well, if it's cooling, then k should be negative because it's decaying, the temperature is decaying, but it doesn't cool to 0 degrees. It would cool to the temperature of the room you're in, of the room it's sitting in. So something like that wouldn't actually work. It does have some type of exponential decay, but it's not exactly like this. So that'll be something that's reserved for the second half of the section, but I wanted to talk about that now because especially if you look at typical problems dealing with exponential growth or decay, that's one of them. And you might be inclined to think right away, oh, I'm going to do it the same way. It's slightly different. But what I wanted to do is just kind of describe what I already talked about, which was the common examples modeled by exponential growth or decay. The one thing is that if you're in a situation where it's not certain, it should be described to you in a very direct way. They'll use the terminology something like things that have a constant relative growth rate, because that's what k is. Let me scroll back up, the constant relative growth rate. So you pretty much have to be told those words if it's not an obvious situation. Now, what are the obvious situations? The obvious situations, well, what we're going to take as the obvious situations are things like mass decay or growth. Pretty much 99% of the time we're talking about mass, we're talking about decay because we're thinking about radioactive decay. Now, the way you can understand why this would follow exponential decay is that the more mass there is, the more that decays. So if something has a half-life of, let's say, 1 year, if you start with 100 kilograms, after 1 year, that means you're going to have half the amount, which is 50. But then after another year, you're going to have half of that 50, which is 25. So the amount you lose is half, but it's relative to the total amount you have. And then continuous compound interest. If you have, the more money you have in a bank account, I think this one's probably easier to understand than radioactive decay, because we pretty much everyone can relate to money, is that if you have a bank account that gets, like, let's say 3% interest, just throwing out a number there, if it's the more money you put into it, the more interest you're going to garner. And that's exactly what exponential growth or decay models. The more or less of something you have, the more or less it grows or decays. Okay. So before finish this kind of introduction part, I wanted to work one problem just so you can see everything. The main thing to take from the above is the formula for y of t. And for this first problem, I'll just go ahead and write it down. But I wanted to point out just the key thing in the problem, why you know you're going to use that formula. The number one says a population of protozoa develops with a constant relative growth rate. So very direct here of 0.8877 per member per day. Now, if you're not familiar with protozoa or you're not familiar with anything, you just really want to take this number because this would be more like an application to biology. Not everyone's going to do biological things, but we just want to take this number. Its constant relative growth rate is that. Well, what does that represent in our formula? That's representing K. We're told K is 0.8877. But more importantly, by being told that we have a constant relative growth rate, that means specifically we are using the formula for exponential growth or decay. Y of t equals y of 0 e to the kt. And now it's up to you what letter you use. If you're using population, maybe you want to use P instead, but we're not told what letters to use here, which means we can just use whatever we want. Okay, so I have this figured out just from that first sentence. It says on day 0, the population consists of 4 members. Well, what is that telling us? That's telling us that y of 0, because population on day 0, that's exactly what this represents. Y is representing the population and 0 is representing the time at 0, is 4. Well, the great thing about our formula is that you'll notice that we've already figured out pretty much the main thing. If you ever want to figure out y of t as a formula, the thing to know is that t is your variable, so that should stay t. You might use it to figure out the missing parts, but ultimately it's your variable. The y of 0 and the k is what we want to figure out anytime we use this formula. So we want y of 0 and k every time to make our formula. That's pretty much the main way I think about word problems is if you're not given the formula itself, which in a calculus class, you're pretty much never going to be given the formula. If you can derive it, especially with exponential stuff like this, if you write down the generic formula, then for this one, it's telling you, well, over here, our variable is t, so we aren't going to be solving or plugging in something for that, but we can and should get numbers for y of 0 and k. And luckily for us in the problem, it was given to us directly. So what I like to do as soon as I figure out or realize that I have both of these is plug them in and we get our formula to use. Y of t equals y of 0, which is 4, e to the k, which is 0.8877 t. And this isn't the answer because I haven't even got to what they're asking yet, but this is going to be the equation we use or the model we use for the entire rest of the problem. So a lot of times figuring out the equation you're using is the hard part. After you figure it out, it just boils down to, well, now we have y of t and we have t. It's going to tell me one of them and I'm going to have to figure out the other one. All right, so this one, what are we asked to do with this? We're asking, what will the population be after 5 days? Well, we know t is representing the number of days because it's per day. So t is the number of days. This is telling us plug in t equals 5 because we want to know the population, plug in t equals 5 and solve for y of 5. Right? But once we got this formula figured out, that's not bad at all. We got y of 5 equals 4e to the 0.8877, and then in place of t, we have 5. Now, I wouldn't try to simplify this just because normally I would try to simplify the exponent to make it easier to type in my calculator or whatever I'm using. However, because this number isn't so nice, I'm just going to type it in all at once. But one thing I want to try to remind you of that I probably mentioned before, but if you are typing an exponent in a calculator, if it's not just a simple number, so this, we have a multiplication, put it all in parentheses. So I have 4e to the 0.8877 times 5 power. Now, one thing I want to mention about this problem is it doesn't really state how to round, but a population, whatever it is, it can be bacteria, protozoa, whatever protozoa may be, maybe we have no idea what it is. It could be people, but populations are pretty much always rounded to the nearest whole number. So if you're not told for a population where to round, just assume it's the nearest whole number. And this rounds to 339. So our answer here, our population after 5 days would be 339. Now for this one, this was as I'll say it's just about as easy as we can get. We'd only had to read the problem, realize, okay, we are actually giving the two things that we need to know, and then we plug them in along with our t, and we could solve it. The rest are going to be a little more challenging, but we'll save that for the next video, and I'll see you there.